Graph similarity using PageRank and persistence homology. So today I'm reading this paper. It's from Mustafa Hajij, Elizabeth Munch, and Paul Rosen, University of Florida, Michigan, KLA Corporation. Abstract. The PageRank of a graph is a scalar function defined on the node set of the graph, which encodes node centrality information of the graph. In this work, we utilize PageRank function on the lower star filtration of the graph as an input to persistent homology to study the problem of graph similarity. By representing each graph as a persistence diagram, we then compare outputs using the bottleneck distance. We show the effectiveness of our method by utilizing it on two shape mesh datasets. PageRank. In this work, we utilize PageRank vector in conjunction with a tool available in persistent homology to define a graph descriptor. More specifically, we view PageRank as a continuous scalar function defined on the vertices of the graph and utilize this scalar function to introduce a filtration as defined in traditional context of persistent homology. We show that the persistence diagram induced by this filtration can be utilized for graph similarity. Conclusion. In this work, we have illustrated how PageRank can be utilized in conjunction with persistent homology to study graph similarity and demonstrated our results on small datasets. In future work, we are planning to conduct a more thorough analysis with larger datasets. Moreover, the PageRank is typically defined on directed graphs. This feature of the PageRank vector can be utilized to induce a filtration that is sensitive to the directionality of edges and directed graph. We are planning to investigate this direction in future. So thank you very much for listening. This was the overview of the paper. Now I will go into more detail. Don't like this video and never subscribe. And now I continue. You already got the juice and the spice of the paper that must flow. So now is the more detail. Introduction and literature review. The problem of studying similarity between the graphs has attracted much attention recently in the pattern recognition and machine learning communities. One of the main challenges is to construct an effective similarity measure between the graphs that takes into account the complexity of the underlying structure while still being computed efficiently. In this work, we utilize PageRank vector in conjunction with a tool available in persistent homology to define a graph descriptor. More specifically, we view PageRank as a continuous scalar function defined on the vertices of the graph and utilize this scalar function to induce a filtration as defined traditionally in the context of persistent homology. We show that the persistent diagram induced by this filtration can be utilized for graph similarity. Persistent homology provides a robust set of tools for the theoretical and practical capacity to understand the shape of the data in any number of dimensions and on multiple scales, placing the concept of shape as applied to data analysis on a solid mathematical foundation. On the other hand, the PageRank function of a graph stores information regarding the centrality of the information of the underlying nodes. The filtration induced by PageRank provides a method to decode information encoded in this scalar function and stores it in persistent diagram. The latter, when combined with the bottleneck distance, can then be used for a graph similarity task. Utilizing PageRank vector has two main advantages. First, the PageRank was originally designed to compute efficiently on very large graphs. Second, as we will show here, as a function defined on the nodes of the graph, the PageRank vector stores rich structural information about the underlying graph that can be utilized to detect similarity between two different graphs effectively. Graph similarity lies within the realm of pattern recognition and machine learning. Persistent homology have been proven to be powerful tools for topological signatures of data. In the study of graphs too, and time-varying data, among others. The efficiency of PageRank vectors has been studied extensively. The PageRank vector has found many applications, including graph partition, image search, and citation analysis, among others. Background. In this section, we give a brief review of persistent homology and the PageRank vector. While the work here is concerned with graphs, we choose here to introduce persistent homology for simplicial complexes, since our work can be generalized easily to more general domains. We assume the reader is familiar with the basics of simplicial homology. Persistent homology. Let K be a simplicial complex. We will denote the matrices of K by V of K as we order sequence of all simplices in K, such that for simplex sigma in K, every phase of sigma appear before it sigma in S. S induces a nested sequence of some subcomplexes called filtration. S induces a nested sequence of subcomplexes called filtration. So phi is equals to K0, which is subset of K1, which is subset of Kn equals K. A D-homology class alpha in H of D of Ki is said to be born at the time I if it appears for the first time as the homology class in D of D and Ki. A class alpha dies at the time j if it is trivial HDKJ, but not trivial in HD of K j minus 1. The persistence of alpha is defined to be j minus I. I think I saw this before, but let's continue. Persistence homology captures the birth and death events in a given filtration and summarizes them in multiset structure called persistence diagram. Specifically, the persistence diagram of a filtration phi is a collection of pairs I and j in the plane where I and j indicates the homology class that is created at the time I in filtration phi and killed entering time j. Persistent homology can be defined given any filtration. For the purposes of this work, the input is a piecewise linear function f from k to r defined on the vertices of a complex k. Furthermore, we assume the function f has different values on different nodes of k. Any function induces low star filtration as follows. V equals to V1 to Vn to be set of vertices of k sorted in non-decreasing order of their f values, and k sigma max has lowest star filtration. So ki equals to sigma nk, which is a maximum, I guess, subset of v's where v is a maximum of f in a sigma for vectors in a sigma, such that the it is smaller than f of vi. The lower style filtration is defined as filtration f of k is a phi equals to k0, k1, subset, kn equals k. The lowest star filtration reflects the topology of the function f in the sense that the persistent homology introduced by the filtration 1 is identical to the persistent homology of the sub-level sets of the function f. Denote by PFK to the persistence diagram introduced by the lower star filtration phi f and k. Furthermore, we will denote p kf to the kth persistence diagram introduced by lower star filtration. In this work, we will only consider the zero-dimensional persistence diagram. Finally, given two persistence diagrams, we measure the distance between them using the bottleneck distance. Namely, given two persistence diagrams x and y, let ni be a bijection between the points in the diagram. The bottleneck distance is defined as w infinity x and y equals infinity ni infimum ni is a map from x to y of supremum x of x minus ni of x infinity norm. For technical reasons, usually add to the persistence diagram infinitely many points on the diagonal of each of the points with is counted with infinite multiplicity. PageRank. Well, just to summarize, so if I understand correctly, what they do here is they, when having this function on the vertices of the graph, they sort of create these subsets of vertices which have some value lower than something, and then between these subsets they define the subsets are this persistence homology, am I right? No, these subsets are the filtration, and then I guess they will look at the homology of those different subsets. So, and also they define distance between persistence diagram as this sort of, I'm not 100% sure, but this bottleneck distance, I think that relates to the fact how, so if you, so bottleneck distance between two points, two vertices on a graph, I think is the sort of maximum, sort of, no, it's the minimum of the available edges when you travel between the 2 points that are available. Sort of, if you would imagine that as a flow of water in pipes, then I think the minimum available, sort of the maximum flow in the graph gives you the bottleneck distance, maximum flow between the pipes available between the 2 points. So the PageRank. This very cute analysis is the lower star filtration introduced by PageRank function in free. More specifically, we consider a version applicable to the undirected graphs. The PageRank function R from V to R is defined for every vertex V by that's the definition of PageRank, where they also use damping factor. A high PageRank score is typically means that the V is connected to many nodes, which also has high PageRank score. For our purpose, it is important to notice that the PageRank is a continuous function. For example, figure 1 illustrates the continuity of the function on the nodes of the graph on the random geometric graph. Results. To validate the method proposed, we run experiments on 2 publicly available datasets. We use mesh datasets to make a visual comparison between the similar graphs. In both experiments, we compute persistence diagram of each mesh obtained from the lower star filtration induced by the PageRank vector defined on that mesh. Pairwise bottleneck distance is then computed between every pair of the persistence diagram. Finally, the resulting discrete matrix is a metric space visualized in 2D TSNE projection. The first dataset consists of 60 meshes and divided into 6 categories: cat, elephant, face, head, horse, lion. In each category, 10 triangulated meshes. Sitting in the dataset. Notice how meshes within the same category are clustered together. We also notice that the meshes with similar topology tend to be closer than those with a different topology. Observe the instance of the clusters of horses and cats. So the cats are here on the bottom right, and horses are on completely different place. Wow, it's kind of surprising. Head is on different position. What do you mean? Head is a different position than face? Interesting. But still kind of close together. And elephant, yeah, it's like there are 2 little data points, and lion is also separate. Well, it's interesting that especially the lion and the cat has very different locations on this TSNE plot. Conclusion. In this work, we have illustrated how PageRank can be utilized in conjunction with persistent homology to study graph similarity and demonstrate their results of small datasets. In the future, we are planning to conduct more thorough analysis with larger datasets. Moreover, the PageRank is typically defined on directed graphs. This feature of PageRank vector can be utilized to induce a filtration that is sensitive to the directionality of the edges, a directed graph. We are planning to investigate this direction in future. Alright, thank you very much for listening. You made it to the end. I hope you